that's not the button I wanted. Okay, gonna stop that recording, start a new recording. Jamal sees the squiggle, lovely. Jamal, have you subscribed to the channel as well? I hope you have. Okay, rightio. Let's start that again. For the recording, sorry if that seems like a very weird start. It turns out I got 10 minutes into the video and people couldn't see what I was writing. So I'm having to start again. Rightio. So this video we are graphing factorized cubic functions. Okay, so we've already looked at the most general form, ax minus h or q plus k. Okay, which has a standard dilation, horizontal translation, and vertical translation, and it looks like this. It has this key point, the point of inflection, and we move that left and right, up and down, and we dilate by stretching the graph. Okay. For the new form, we're going to graph the polynomial version, okay, the full ax cubed plus bx squared plus cx plus d. Now the way we graph this is by factorizing it, so finding all of its x-intercepts and also finding its y-intercept. And when we do that, depending on how many x-intercepts there are, it's how we define these three different types of graph, is by how many x-intercepts there are. We can have either this first form, okay, which is a one-intercept, one x-intercept right there. So it can come down, has a bit of a turning point here, goes back up, has a y-intercept, and then down through the one x-intercept. We can have another version of it, which could be coming up the other way, down, and then up that way. Okay, still only has one x-intercept. The second type is a graph that has two y-intercepts, x-intercepts, sorry, okay, where one of them is a turning point, okay, and then the other one is a proper through intercept. Okay, so when we have this two intercept version, it's also sometimes called a repeated factor. Okay, where this turning point here, if we factorize this, would look like x minus 1, and the turning point is whenever we have two factors that are repeated. So we might also have something that looks like x minus 2, x minus 2, x plus 1, whatever. When we factorize, it looks like that. Since we have two repeated intercepts, that means that repeated intercept is actually going to be a turning point. Okay, and then this third one will just be a normal intercept. Okay, and then the very last one is, that hasn't broken anything. The very last one is a three intercept, 1, 2, 3. Okay, now it can come up, go down through, we have a y-intercept there, but then we have our 3x intercept. And now what determines if it's going to be a 1 intercept, 2 intercept, or a 3 intercept are the terms a, b, c, and d. Okay, you can't really tell when you're looking at it in polynomial form, where it's in this full expanded form. You can't tell just by looking at the numbers what it's going to be, if it's going to be a 1, 2, or 3. You have to factorize it first and see how many factors you get. That will then tell you if it's a 1, 2, or 3 intercept cubic function. So there is that. The other way that we could have this one, well, again, is it could be flipped upside down, as if we had a negative. If you had a negative a, it would flip it upside down like that. So let's have a quick go at graphing one of these. And the nice thing is, this first example, we're starting already in factorized form. It's in factorized form, and we have 1, 2, 3 factors, and they are all different. Therefore, it means we're going to have a 3 intercept cubic. Okay, and remember, when we talk about intercept, I'm talking about the x-intercepts. So how do we find those? We use the null factor law. Okay. Null factor law. So we get x minus 1 equals 0, or x plus 2 equals 0, or x plus 1 equals 0. I just want to make sure that's still appearing. Yes, it is. Okay, so from that, therefore we get x equals 1, or x equals negative 2, or x equals negative 1. So we can plot those in. I'm going to just mark these with green, these intercepts. So we get the first one at 1, 0. That one there is at negative 1, 0. And our last one was at negative 2, 0. Okay. So we have our 3 intercepts. Now I'm going to do a quick little sketch up here. We can have a think of, there's going to be 2 different ways this could appear. It could be a positive or negative cubic, and you'll see in a second what I mean by that. Okay. One of them, okay, we can start with a positive gradient, come up, flip around, go back up that way, and end with a positive gradient. We start with a positive, we end with a positive gradient. Okay. We could have that way, or we could have it the other way. Start with a negative gradient, come down, turn, back around, and out. Okay. So started with a negative gradient, ended with a negative gradient. Now, which one is this going to be? Well, the quickest way and useful, because we need to graph it anyway, is find our y-intercept. Okay, so let's find our y-int. So let x equals 0, so we get y is equal to x plus 0 plus 2 and 0 plus 1. And that's going to give us negative 2. So we can plot that down here. Okay. So now that we have that, the only way that we can connect 1, 2, 3 dots is by coming down through that one, up through that one, and then keep going. Okay. So if this keeps going up and up, that means we have this first case. This is going to be a positive gradient, and as we go through this dot, the only way to get through our original first dot is we have to turn around and come back down. Okay. So we have that. From here, okay, there's a couple things I want to point out. One, this turning point here and this turning point here, okay, we don't have to find them. It says no need for it. Okay, and 2, unlike quadratics, they aren't always halfway between intercepts. If we go back to the previous slide, we can see this turning point here, okay, is definitely not halfway between negative 1 and 2. Okay, that should be over here. Okay, and same on this one, it's skewed off a little bit to the left. Same over here, that's skewed off. Okay, all the turning points aren't actually halfway between the intercepts. Unlike quadratics, that doesn't occur. There isn't a way to find the location of the turning point until I teach you how to do a topic called calculus. You could do trial and error and find where the number gets its highest in this zone between negative 2 and negative 1. You could try there, try there, try there, and get a rough estimate where it is, but there's a more exact way using a topic called differentiation and calculus, and we could find the exact coordinates. But for now, we don't have to actually worry about that. So there was a sketch. There is 2 other ways though to know if it's going to be a positive cubic, okay, if it's going to look like this, or if it's going to be a negative cubic, okay, before finding the y-intercept. The first and easiest way is looking at your cubed term. Okay, so every polynomial we have our cubed term. Okay, if a is greater than 0, it's going to be positive. Okay. If a is less than 0, it's going to be a negative graph. Okay, if a is positive, we can think the graph's overall going up. If a is negative, we can think overall the graph is going down. So that is really simple, and I could know that straight away looking at my x terms. If I did x times x times x, well, that's going to give me x cubed, which has a positive 1 as my a. So I knew straight away looking at this in factorized form, I knew it was going to be positive, so I didn't even need to define that to get a sense of the graph. So that's one way. There is a third way. It's more convoluted, takes a few more steps, uses a little bit of trial and error, okay, but it allows us to create a sign diagram, okay, and sign diagrams are actually really useful, and you could think of them as a simplified inequality almost. We could use these to help us solve inequalities. When is y less than 0? When is y greater than 0? It's sort of a simplified, flattened out version. And it's saying the whole point of this is we have x going across horizontally, and then our vertical is our y. Is it positive or is it negative? It doesn't care if it's really positive or really negative, like is it positive 5 or positive 2 or positive 1? Okay, we're not sketching like this at its different points. We just care, is it positive? Okay. Or is it negative? And when does that always change? That changes at the intercepts, okay? So this is an example where we have 3 intercepts at A, B, and Y, okay, or alpha, beta, and gamma. Technically is what those symbols are, and we can see we have a negative sign in front, so that means it is going to be a negative ax cubed, so we know it's going to be going down, which it's drawn as here. Okay, so we can look at this, go, okay, it's going to be negative, so that means to the furthest left of the first intercept, my graph is going to be coming down. We know it's going to look something like this. I have my 3 intercepts. Okay, so it's going to start in the positive y zone. We're starting in the positive y zone. We get in the negative y zone, which is this. Okay, we get back in the positive y zone, which is this. And then we finish off with back in the negative y zone. So a sign diagram shows, are we in positive y or are we in negative y? Or are we above the x-axis or are we below the x-axis? Drawing these diagrams without showing you how to do it can be a little tricky, so I think it's easiest if we just jump straight to an example and show you how to do this. Okay, so find the factors of y equals x cubed plus 2x squared minus 5x minus 6. Hint, use the factor theorem and long division. So let's try the factor theorem. So we need to use a factor of -6. Okay, so I'm going to try, let's try 1 straight away. Okay, so y of 1 is equal to 1 cubed plus 2 by 1 squared minus 5 by 1 minus 6 is equal to 1 plus 2 plus minus 5 minus 6. That's no good. No good, so let's try y of -1 plus 2 by -1 squared minus 5 by -1 minus 6 is equal to -1 plus 2 plus 5 minus 6 is equal to 0. That did not equal to 0 up here. This equals to 0. Happy days. We have found a factor theorem. Or we found a solution. Okay, so we can say x equals -1 is a solution. Therefore, x plus 1 equals to 0. Or x plus 1, sorry, is a factor. So now that we have a factor, we can do the long division. Okay, you could keep using the factor theorem. You could keep trying different numbers. You could try -2, -3, 3, +2, 6, -6. You could keep trying them to try and find the other factors, or you could go straight to long division, or you could use the factor theorem. I'm going to use the long division because I always think it's something that everyone needs to practice more of. I'm not going to talk while I go through this. It'll just be quicker. Okay, so that all worked out. We got no remainders, so we ended up with, I'm going to have to use some space over here. Actually, I'll go up here. We've ended up with x plus 1. I haven't done that far enough across. X plus 1, x squared plus x minus 6. Okay, so there was our solution to long division. So I can now further factorize that using inspection. I'm going to try and factorize the quadratic. So the -6 gives me plus 1. So that'll be plus 3 minus 2. 3 times -2 is -6. 3 minus 2 is plus 1. Okay. So I've factorized it. My function is now y equals x plus 1, x plus 3, x minus 2. Okay, so what are my intercepts? Well, we could use the Null Factor Law, but to shorten that up, we get x equals -1, x equals -3, x equals 2. Okay, so there are intercepts. So to now create a sign diagram, I'm going to put them on my sign diagram. Just mark intercepts. So you could put some values, a scale if you wanted to, if that helps. So I'm going to call that 0, 1, 2, 3. Okay, and now I'm going to mark them on. So x equals -3 there, and I just put a big through line, big vertical line through wherever they occur. Okay, because that's where my graph is going to cross the x-intercept. Okay. And now the second stage, okay, is finding what are my lines that I'm going to use to connect them. When is the graph positive? When is the graph negative? Okay. We could use our trick. Okay, sorry, I should say not when the graph is positive or negative, when the y value is positive or negative. Okay, we could use our trick of looking at a x cubed term, okay, and is it positive or negative? But the purpose of using these sign diagrams is let's do a little bit of substitution. Substituting a point in between each of the zones, okay, and find out what the value is. Is it going to be positive or negative? Okay, so let's go y of 0. Let's start with that first up. That's really easy because we're going to put 0 plus 0 minus 0 minus 6. So it's just going to equal -6. So at 0, our y value is equal to -6. And the important part of that is the negative. Doesn't matter what that it's 6. It's just that it's negative. Okay. So our y, is it positive or is it negative? At 0, it is negative. Okay, it's down here. So I can now draw this as, in that whole zone, my y values must be negative. They can't get back to positive without crossing through the x-axis, which only occurs at the intercepts. So that's that. From here, you can make a reasonable guess that that's going to be across there, that's going to be across there, that's going to be across there. But let's double check. Let's go y of halfway between these two zones, let's go -2. So we get -2. cubed plus 2, negative 2 squared, minus 5 by negative 2, minus 6 is equal to negative 8 plus 4 plus 10 minus 6 is equal to 14 minus I've done something wrong there. Yes, negative 2 squared is 4 times by the 2 is 8. Yeah, there we go, that's better. 18 minus 14 is equal to positive 4. Okay, and just like before, we don't really care about the number, we care is it positive or negative. We got a positive 4. Okay, so in between negative 3 and negative 1, our graph is going to be positive. Okay, and then it crosses, well, from then on, our graph is going to be negative, and off this end, it's going to be positive. Okay, so that is a sign diagram. It's telling us are our y values positive or negative and what zones they're occurring. Then once you have that, you could then use them to draw your graph. Okay, so continue the sign diagrams. Using the sign diagram, sketch the cubic. Okay, so let's go back. Our intercepts are at negative 3, negative 1, and positive 2. Okay. We then knew it was positive greater than 2, so it needs to be going up like that. We know it was positive between negative 3 and negative 1, so it must be doing something like that. Less than negative 3 down this way, it was negative. So my graph is going to go like that. And the last thing would be drawing in this final connection, but I'm not going to draw it in until I know the very last thing is my y-intercept. Let's find my y-int, and I actually already found it because I did y equals 0 back here. Y is 0 equaled negative 6. Okay, so 1, 2, 3, 4, 5, 6, way down here. Okay, so this actually needs to be a lot steeper. Okay, so that is very roughly, there's our intercept. I'll put the y-intercept in different color. Okay, and same thing, we can't assume that that's where our turning point is. That was 0, x6, that was -1, 0, -3, 0. Okay, so sketching cubics can be a little messy, and doing on this tablet I can't erase at the moment, so that's a bit of a pain. But getting the idea how we could use our sign diagram. Okay. It's much more intuitive using just recognizing which way it's going to be rolling through. Okay, using this idea of what's our a, is that my a greater than 0, whereas my a less than 0. It's much more intuitive once you recognize and get used to the pattern and shape of what cubics are going to look like. But sign diagrams, you do need to know how to use them because they do get used in applied cubic work. And 2, they are really handy to avoid yourself getting into trouble when you're dealing with repeated roots. Okay, because a sign diagram for a repeated root would look something like this. The graph would actually be negative, come up, it touches the x-intercept, comes back down, stays negative, and then goes through. Okay, if you just assume using this whole idea of the a with the repeated root one, then you might make mistakes. Okay, right, and here's a great example. If a factor is repeated, e.g. y equals x minus 1 all squared, x plus 3, then there are only 2 intercepts, and the repeated factor is also a turning point. Sketch y equals x squared bracket x minus 1 by first making a sign diagram. Okay, so what are our intercepts? Well, this is really, this x squared in here, I could rewrite this as x minus 0 all squared, x minus 1. Okay, so our first intercept is at x equals 0, and the second one is at x equals 1. So, go to our sign diagram and put those in. All that. I can't undo that. It's annoying. We'll call that 0. Actually, see if I can erase. Yep. Okay. Now is my pen going to have it whack out? Yes, it is. There we go. Okay, that's why I don't like erasing, because my tablet has a whack out. Okay, 0, 1, 2, neg 1, neg 2. Right, intercepts at x equals 0, and that's this one here. Okay, times 2. It's a repeated root. Okay, so that is going to be a turning point there as well. And then x equals 1. So I can draw a line through x equals 1, and I'm actually going to draw a dot at the repeated root because it doesn't go through, it just touches. Now, is it positive, is it negative? Which side of my sign diagram and am I going to be for my y values? Well, let's substitute in a point. Let x equal somewhere to the left. Let's go negative 1. Y is going to be equal to neg 1 squared. Neg 1 minus 1 is equal to negative 1 squared is 1 times by negative 2 is going to be negative 2. Okay, so importantly, it is negative. So I can now draw my sign diagram. Over this side, it is negative. It gets to 0. It's going to come up and touch. Okay, it's touching. It's going to come back down because it's a repeated root, go across, go through the next intercept. And that's what my sign diagram is going to look like. Okay, so now we can sketch it. So my repeated root is at 0. I have an intercept at 1. So my graph is going to come up, touch, come down, and go back up through. Okay. So the shape stays the same. It just happens to be that one of the intercepts is a repeated root. And that's how we sketch that. Right, now the last one is if we have a 1 intercept. So we've sort of worked backwards here. We started with 3 intercepts, then 2 intercepts. So 2 intercepts, okay, is the repeated one. And now we're looking at 1. Now 1 is if the factor is repeated 3 times, or we get x minus 1 and then this quadratic, okay, quadratic can't be factorized. Okay, we can't factorize this, so that means it just has 1 root. Okay, now I'm not going to do the cas part of this. I'll leave you to do the cas part. The function for that is max or min. Okay, you want to use those two in your cas to find what the max or min is. But we have a negative x minus 1 x squared plus 5x plus 7. Okay, so the factor, the intercept, is at x equals 1. So that's there. Okay, and it's a negative. Okay, so if we remember, a negative cubic comes down, up, and goes down. Gradient starts negative and finishes negative. Okay, and if that's my point, well, I must be going through it like that. It's going to come up and do something like that. Okay, now the actual locations of that bit and that bit you can find using your CAS, but we know that that is going to be 1, 0. And the other point that we want is our y-intercept. So let x equals 0. We get y is equal to negative -1, 0 plus 0 plus 7 is equal to 7. So that point there is 0, 7. So there is a one-intercept graph, one x-intercept graph. That's it for this exercise. I will hang around if you want to type in any comments on YouTube quickly. There'll be a little bit delay before I appear them because of the stream delay, but happy if you want to ask any at the moment. Well, if you do think of any, you can ask me on Edmodo, that's completely fine. Or put them in the chat to this video, that's fine as well. Otherwise, I will finish up there.